I'm Neil deGrasse Tyson, your personal astrophysicist, and this is the Cosmic Queries edition. I have with me Leanne Lord. Leanne, welcome back to Star Talk.
Hey.
And this is Cosmic Queries. It's not your first rodeo here.
No, not at all. I'm experienced.
Thank you. And so to remind some listeners, perhaps or tell you for the first time, in the Cosmic Queries editions, we solicit questions from all of our web presence, our social media presence, and a comedian, in this case you, call through them and just send them my way.
Yes.
And so let's go ahead and do that.
Okay. And we do remind people that you have not seen these in
I haven't
advance.
seen. No, the point is not to stump me or anything.
No.
It's just I haven't seen them. So if I don't know some, I'll just tell you.
You're not just gonna make it up.
I
okay.
can do that too.
If you pass, I'll answer it. What? Oh,
Exactly.
That's a disaster.
Yeah. Leanne, you take it. All right.
Crickets.
So what do you got?
Okay.
So this is probably potpourri. I mean, we're not one subject or all. It's just on all the universe in this segment.
We are, I guess, discussing dark matter and dark energy.
Oh, dark energy. Oh, that's fine. Okay.
And I at first took it personally until someone said, "No, we're not talking about you."
Okay.
So the first question is from Rocky Kofrin. And
gotta admit, that's a cool name, Rocky.
It is. Yeah. It is pretty cool. And I actually now don't know if that's a he or she.
Is that through what social media source did that come?
I believe this is from Facebook.
Facebook, good.
Because if it were Twitter, it would be only 140 characters.
Okay.
So it's a little longer than that.
That's a long question. Go for it.
That's a short question. Okay. I've seen graphs and heard percentages of what makes up the universe. Somewhere around 80% dark energy, 16% dark matter, and 4% everything else. My question is, how did we come to these numbers? What instruments were used to make that conclusion?
Nice. Well, first of all, I mean, dark matter is most of the gravity we measure in the universe has no known origin. Everything we know that makes gravity, like matter and gas clouds and energy and all these things, you add it all up, it doesn't account for all the gravity we see. So that's like the dark.
So there's missing stuff.
It used to be called missing matter. Okay. It used to be called that. And we say, well, how do you know it's missing? How do you know it should have been there in the first place?
Right.
So it's really too much gravity is what we should call it, not missing matter. Because maybe gravity comes from other kinds of things. So you can add up how much of that is driving the universe.
Okay.
Right? And put that in a box. And then you say, hey, the universe wants to sort of slow down in its expansion because there's all this gravity, yet it's accelerating in its expansion. There's some mysterious pressure in the vacuum of space pushing on the universe. That takes a certain amount of energy to do.
Okay.
You put that in a box. You add those two together, it is 96% of everything that matters, no pun intended, in the universe.
Okay.
And so everything we know, all of our laws of physics, all of our understanding of the behavior of matter, motion, and energy is 4% of the universe.
We understand.
We understand 4% of the universe. Of what's driving the universe. And that's the chart. This is a pie chart. It cut away 4% of an apple pie. That's all you got. That's all you got. And the rest, we know it's there. And one of the questions was, how do we know how much it is?
How would we get to this?
You can measure how much gravity is out there because you can see the motions of objects. All right. And you can see how fast, for example, we are orbiting the center of the galaxy. You just measure that. We can do that.
No,
right?
of course. Every day.
But of course. And once you find out how fast we're going, you can say, well, how much material is between us and the center of the galaxy to enable us to go that speed? These are two very related numbers. The amount of gravity pulling on you and how fast you're going in orbit.
Okay.
They're connected in a single equation. You calculate it up. You say there should be this much gravity down there. And you count up all the stars and all the gas clouds, all the black holes, everything. And you cannot account for that much gravity.
So there's too much gravity.
It's a too much gravity problem. That's right. That's very cool. That's how we measure that. Now, the acceleration of the universe, we have supernovae, the stars that blow up at the end of their lives, and they're so bright they outshine the entire galaxy in which they're embedded, briefly, like for about a week. So that means galaxies really, really far away, if one of these supernovae blow up, you say, hey, we just saw you. All right.
That was there 15 minutes?
Where was the air? And so you have, and we know how bright these supernova should be, how luminous they should be at a given distance.
Okay.
All right. So like a 100-watt light bulb, put it a mile away. I know how dim that should look.
Okay.
A mile away, half a mile away, right in front of your face. You do this with supernovae. I know what at whatever distance we find, I know what it should be. When you do that, what you find is that these distant galaxies are accelerating away from us. They're accelerating away.
Oh, I get it.
So because these are like our standard candles, that's an expression you don't hear much anymore, but it's the metric that we use to know how far away an object is how dim the supernova is.
Right.
And so when we lay it all out on a graph, we find out that where it is versus how long it's been traveling don't match up, and so that had to have been accelerating to get there. And so you add all that with, we only know 4, so we're dumb, stupid, ignorant about most of the universe, which is really cool. Keeps astrophysicists employed.
And doing shows called Star Talk.
Star Talk, after hours.
Wow.
That's a long answer, but it's a lot of the universe to get in there.
Dude, you condensed it so well. That's an entire semester for some of us.
Yeah, it actually, sure. Yeah, 96% of the universe put into 3 minutes. Yeah.
Wow. Well done. Only our personal astrophysicist can do that. I have a sort of related question from Gene O'Donnell. Who discovered dark matter? And I know it wasn't Al Gore. Sorry, Al.
Yeah, he discovered it on the internet.
On the internet.
Yeah, so dark matter was discovered in the 1930s by a dude named Fritz Zwicky.
Not Fritz.
That's totally Fritz.
Oh, man. Could that dude party? When did he have time to discover dark matter? That dude was always at a party.
So he was Swiss-born, American. I don't know if he was ever naturalized, but his whole professional career was in America. And he worked at Caltech in Pasadena, California, the California Institute of Technology. And he was measuring the movement of galaxies. Now, the example I just gave was with the sun in our solar system orbiting the galaxy. He did that same measurement for galaxies orbiting one another in a cluster of galaxies. So he's measuring how fast these galaxies are moving, and it says the speed they're moving tells me how much matter should be there to account for the gravity. And he does the calculations, and he's off by a factor of 5 or 10. Right, and he's double checks and triple checks his calculations, they continually don't match. And he said there's missing matter somewhere, and it was the beginning of the missing mass problem, today known as dark matter. Cosmic Queries edition, and I got Leanne Lord with me. Hey, Leanne.
Hey, yeah, we're early in on this, but already my head is starting to hurt. I'm trying to wrap my mind around dark matter, dark energy. Fritz.
Fritz, we ended talking about Fritz.
Mr. Zwicky. I'm sorry, let me be respectful. Mr. Zwicky.
It'd be Dr. Zwicky to you.
Dr. Zwicky. I'm sorry, sir.
Fritz Zwicky discovered dark matter back then. He was called missing mass. It was called the missing mass problem.
Okay.
And it's the longest unsolved problem in modern astrophysics.
Oh, and not what women are thinking? Really? Okay.
No, that would be a longer problem. Can I give a related comment to that, if I may?
It's your show, so yeah.
Okay. The study of the universe is the second oldest profession. Okay.
Seriously?
So both of these challenges go way back.
Okay.
Fritz Zwicky was quite a colorful character, and with a name like that, how could you not be?
Yeah.
And he was cantankerous, and he would scream at you and pound the table if he didn't agree. But he was brilliant, and he predicted the existence of pulsars, which are rapidly spinning balls of neutrons. And so we should call them Zwicky stars, really, in his honor.
I like it.
But they would later be discovered, and he had predicted them based on what he had just learned from the newly invented branch of physics called quantum mechanics. So that's Fritz Zwicky. Cool dude.
All this because he couldn't figure out women. He goes, forget it. I'm going to figure out the galaxy.
Exactly. That's easier.
It's easier.
All right. So what else? So this is giving you a headache. We'll try to lift that somehow.
Yeah, no. It's
right.
I know when I am playing outside of my intellectual depth, and I am not afraid to admit
We
it.
will make it part of your depth. So
That's why I come here.
Bring it on. So I haven't seen these questions. You got them off our social media circles.
Yes. Well, our next question is from Andrew Schaefer, and it's similar but different, I guess, of a kind. It's how much dark matter or dark energy is predicted to be in the universe.
Well, so the number that we put forth, so let me back up. We measure the stuff. Right. And so it turns out when we try to make galaxies, on a computer.
I was about to say, did you just let me in on some top level stuff that I am not cleared to hear?
We have, that slipped out.
There are men in dark suits coming in. Hello, gentlemen. What? I didn't hear anything. What?
Look at this light. It turns out before we understood how deep the dark matter problem was, we had a hard time making galaxies on a computer. You put in matter, you spin it up, you see if it's self-gravity, because matter attracts itself. You watch the computer, provided all your formulae are accurately captured in the program. Newton's laws of motion, differential equations that track where things move, and you put it all in there. You load it up, and we found out we can't make galaxies. Not only that, we can't make the structure of matter in the early universe unless we put dark matter in the equations.
So something was missing.
Something was missing. And so not only does the universe show us it has dark matter, we need it in our formulations of the universe in order to create a universe that looks like the one that exists. So we have good theoretical confidence as well as observational requirement that dark matter is out there.
And we think that missing thing is dark matter and not love. You need love to make a universe.
An absence of love. No, it's too much love. It's more gravity than we can account for.
Okay.
There it is.
All right.
So what else you got?
I have a question from Robbie Jaeger or Jaeger.
From where? From what source?
Robbie does not identify where he or she is from, so it might be a witness protection thing, but still has a quest for knowledge. I have heard that dark matter and dark energy make up the majority of stuff in the universe. Is the mass of all the black holes within galaxies figured into this calculation of stuff?
Oh, black holes are ordinary stuff.
Oh.
I mean, they're exotic for in our lives.
Right.
But for this 4% of the universe, we got all the black holes, I promise.
Oh, so they're in there.
We totally
got
the
4% of things that we get out of the apple pie slice of our understanding.
Yeah, so that's why dark matter is really not a good term. We should just really call it Fred, because